the invitation today. I'm Zhongyi Wang, a third year, sorry, third year PhD student in Courant right now and supervised by Adi Rangan. And I'm giving a talk today about the Markovian surrogates to model neuronal dynamics, which is also my recent work. So I will give a brief outline here. So I will talk about spiking neural networks and why we would care about them, and why current methods, including like direct simulations, don't always work. So we might need a more efficient way to simulate or at least approximate some dynamical parameters of spiking neural networks. I will share my Markovian framework and some results we achieved and give a brief discussion. So for those of you who know the history of neuroscience, this is a drawing by Cahal in 1898, the first drawing of the nervous systems as shown as composed by neurons, and they are interconnected with axons and dendrites. And these neurons can be excited, meaning that once the membrane potential of a neuron reaches a threshold, it will release an action potential, or we call it a spike. And that spike will be conducted along the axon, along the entire neuron body, including the axons, and it will be delivered to the next neuron it is connected to, which we call a postsynaptic neuron. And the way the action potential transfers between neurons is typically there's one way that is called a chemical synapse, as shown by the figure below here. So the presynaptic neuron, once it fires an action potential, it will release neurotransmitters into the synaptic space here, and the neurotransmitters will be received by the postsynaptic neuron. And depending on the types of the neuron transmitter, the postsynaptic neuron will be either excited or inhibited. This essentially impacting its probability to fire another action potential. So this is a very brief introduction to spiking neural networks. And in this work, we are mainly concerned about the statistics of the dynamics instead of the detailed temporal dynamics itself. Why would that be the case? What should the statistics tell us? For example, the most commonly used statistics is the average fire rate of the network. So it is an extremely important statistic of a neural system because, as you can see, here is just one of many examples. In this 2006 paper by Zhongyi Wang, they found out that fire rate plays a role in decision making. I will not go into details here. This is just to illustrate why we will care about the statistics of a neural network. And another example of the statistics of a neural network, one step above mean fire rate, is the membrane potential distribution. It is also important in two ways. First, it is actually very experimentally available, as in we can measure, we can read the membrane potential distributions from intracellular recordings. And it is also useful for us to infer some properties about the network itself, as shown in this 2004 work that they're using the intracellular recordings to get the membrane potential distributions, and in turn use the distributions to estimate the synaptic noise parameters or synaptic conductances. So that those are only two examples of why we should care about the statistics of a neural network. Now, why would we propose this Markovian surrogates? What's wrong with the like direct simulation or other methods? Well, there is an intrinsic property of a neural network, of a spiking neural network, that is the spike. So what I'm showing here is the simplest formulation of a conductance-based decay integrate and fire network, which is composed of two populations, one excitatory population and one inhibitory population. So as you can see, the first two equations describe the evolution of its of the membrane potential and the synaptic conductance of a single neuron. Those are not too bad. The first is a perfect ODE. The second, this is delta function, so the second consists of jumps, but they're not too hard to to tackle. But the third, which is the core mechanism of a spiking neuron, is when the membrane potential reaches the threshold here, it will fire an action potential, and its membrane potential will be reset to the rest potential, and it will stay there for a period we call refractory period, and this is non-zero. So the third equation, the firing and reset mechanism, introduces a jump or a discontinuity to this ODE system. As we can see in the figure here, this is taken from the famous textbook Theoretical Neuroscience by Diane and Abbott. We can see the dynamics of the membrane potential here. They are going through this repeated reset, so repeated discontinuity. So first, this discontinuity makes our typical analytical tools for ODEs not really applicable here, not without significant modifications. Secondly, even if we are just solving it using tau leaping or similar ways, we cannot accelerate it and or scale it, because it is very hard to parallelize this system, because this spiking neural network is typically coupled, which means that for every action potential could be delivered to other neurons in the network. Therefore, it is not really parallelizable, because for every spike, you have to communicate with other neurons to see if they receive this spike or not. This makes it not scalable as well, because the checks you need to do for each spike grows exponentially with the computations you need to conduct grows exponentially with the number of neurons in the network. So this urges us to find some efficient surrogates, efficient methods to simulate or approximate our desired quantities, which are the statistics we discussed before. And here is a benchmark by Arne Heitman in 2022. It shows the simulation times versus the network complexity in units of neurons. We can see that the higher they are, the faster they are, and the lower they are, the slower they are. So as we can see, once we get the more neurons we have, the less speed we get from the simulations. But our human brain is very efficient in that way. So this all motivates us to find a framework or find a method to accelerate or to find efficient approximations of the interesting quantities. So I will introduce our framework using a concrete example here. So what we are considering is a two-population EI network, which means that this network consists of an excitatory population and an inhibitory population. the neurons inside each population are identical in physiological terms. So their parameters are the same. And they are interconnected within each population, and the two populations are connected as well. And each neuron will receive an external input. And in order to introduce our framework, we will make two important assumptions. First is that the network is annealed. The architecture is annealed. What does that mean? We can think of it as an all-to-all connection with random synaptic failures, which means that for every single action potential should be received by every other neurons in the network. But it could fail, but each neuron could fail to receive it independently, and with a probability we can control. The second assumption is the rapid decorrelation of each neuron's synaptic drive from its past. So what this means is that we can approximately view the synaptic drives of each neuron to be independent from its own past and from other neurons' synaptic drives. And these two assumptions lead to an important preliminary result, which is that two neurons of the same type and at the same membrane potential are indistinguishable, which means that in order to get the system, the entire network's state, we only need to track the distribution of both potential and conductance. So from this, we construct our Markovian framework. The methods are like 4 steps. First, we discretize the state space. The state space consists of both membrane potential and conductance, so we will need to discretize them both in some way. Second, we can coarse grain the entire network using the assumptions above, so we don't have to track every single neuron state, but rather we can track a distribution. And then we derive the state transition matrices for this Markov process. So the first 2 steps will also establish the Markovian nature of our model. And once we have the state transition matrices, we can either perform Monte Carlo simulations very fast, or we can calculate statistical properties directly from the matrices. For example, we can simply solve for its invariant measure of the transition matrices for the membrane potential distribution. And we can read from the distribution the steady state function rate. So I will introduce how we do that briefly. So first, we discretize the state space. For membrane potential, it is very standard. We just cut them into pieces, into these grids. And initially, the membrane potential can take values from Vi, which is the inhibitory reversal potential, to its firing threshold, and R is a special state which indicates the refractory period, during which the neuron will not respond to anything. And we can discretize as this, where the lowest state corresponds to the reversal potential and the highest state corresponds to the firing threshold. And for synaptic conductance, it is trickier to discretize. We introduce a new concept called pending spike pools, H. So why would we do this? So if we consider the classical conductance dynamics, the conductance will decay exponentially and only get a jump when there are new spikes are received by the neuron, and it will exert its effect on the neuron gradually in an exponential manner. Instead of letting spikes doing that, we are considering this pending spike pools, H, which accumulates discrete synaptic kicks. whenever neuron I receives a spike. And these accumulated discrete kicks exert all of their effects at once after an exponentially distributed waiting time. And another thing is, for each incoming spike, we do not accumulate one discrete synaptic kick, but rather we can accumulate k discrete synaptic kicks. And we can argue that as k goes to infinity, this discretization method will converge to the classical conductance dynamics. So in this way, we can view H, which is our pending spike pools, as a birth-death process, because the increase of H entirely depends on the final rate of other neurons, and the death rate, which is the consumption rate of H, is proportional to the value of H at this time. So now, after we discretize the membrane potential and synaptic conductance, which are the states of the original LIF system, we have our network's dynamic state, which is described by a 4n dimensional tuple. This V here describes the membrane potential of each neuron, and this H describes their respective conductance. Oh, and this HEXT refers to the external, the conductance corresponding to the external input. But in our work here, we set the the time scale of the external input to be 0. So external input will be consumed instantly. They do not accumulate. This is a general description. So after we finish the discretization, we can use our assumptions to do a coarse graining on the network. So recall our assumptions, which is annealed architecture and a rapid decorrelation of synaptic drive from its past. But we need to be careful here because the second assumption is valid. I don't want to say only, but it is valid for fast synapses like AMPA and GABA-A. It might break down for slower than synapses like GABA-B, which is whose timescale is on a scale of seconds instead of milliseconds. So with these assumptions in mind, for two neurons IJ of the same type, their synaptic drive or their pending spike pools can be seen as ID random variables. Also, the inhibitory pending spike pools is independent from the, this should be excitatory, and the membrane potential itself. Therefore, we reach the conclusion that two neurons of the same type and at the same membrane potential are indistinguishable. Therefore, the voltage configuration of the network can be represented by just distributions, which we track instead of the individual neurons' detailed states. Also, we don't have to track the full evolution of our pending spike pools H. Results from the averaging of Markov chains guarantee us only the expectation of the pending spike pools is relevant for coarse-grained dynamics. And now we can build state transitions, which are just from the kicks we discussed before, and from leakage, which brings V one step to the reset, and refractory period, which a neuron will leave refractory period with a rate 1 over tau ref. Sorry, this is 1 over tau ref. So these are 5 events that can happen to any individual neuron. Based on these, we can construct our state transition rate matrices, which is a function of the current expectation of pending spike pools. And once we have these state transition rate matrices, we can have our complete description of network dynamics. So the evolution of voltage distribution follows a Kolmogorov forward equation. And the evolution of expectations of synaptic drive follows the dynamics of the expectation of a birth death process, as seen here, the exponential decay and jumps. And here, the accumulation rate of H depends on the instantaneous fun rate F of the network. And we can actually read out F from both mu and rho at time t. So F is basically the rate at which an excitatory kick is consumed times the fraction of neurons excitable by one excitatory kick, plus the rate of external input times the fraction of neurons excitable by one external kick. And this is a closed system, and we can solve directly for the steady state, or we can evolve it as a perfect ODE. There is no jump included here. So there are some results of comparing our estimator, which is given by this description of dynamics, versus the ground truth from simulations. This is tested on 5,000 sets of parameters by varying different parameters, by varying different dynamical parameters. As we can see here, it is generally good for varying like the synaptic strength S, the synaptic coupling probability P, and the external rate lambda and tau ref. But it is not good for varying the synaptic timescale tau here, because in this very simple estimator, we chose to solve for the steady state directly. And in the steady state, we can see that we set this to 0, so the steady state mu is actually proportional to tau. And in our construction of Q here, the terms involving mu is inversely proportional to tau, so they just cancel out. In order to improve this result, we can actually not to like solve this naively, but we can evolve this until they reach an equilibrium to get better results of estimations, as can be seen here. This is a comparison of our method, the mean-driven limit, as introduced in David Tsai and Trev's paper, and the MF plus V algorithm, which is introduced by Zhuocheng Xiao et al. In 2021. The black dots are our results, and the blue and red dots are the other methods respectively. As we can see here, our method generally outperforms the other methods. For some brief discussions, the advantages of our frameworks is, first, I think the biggest is that it can deal with finite size effects, which means that we do not require the number of neurons in our network to go to infinity. While the typical estimators like neural field, Fokker-Planck, kinetic theories, etc., they have to let the number of neurons go to infinity to function. Otherwise, their weak connection assumptions will not hold. The second is that we can just treat the firing, refractory, and reset as direct state transitions. This addresses the obstacle of discontinuity because it doesn't present an obstacle in a Markov chain at all. They're just state transitions unlike any other. And incorporation of higher order dynamics leads to improved accuracy, as can be seen in our two figures here. Once we incorporate the dynamics of mu properly, we can improve our estimation accuracy. And I introduced our framework using the simple example of leaky integrant and fire, but it theoretically can be expanded to accommodate any single neuron dynamical model. We just have to change our method of state space discretization here. But it also has some serious limitations. First, we have to assume the architecture is annealed, so no neuron is favored over others. Therefore, if the network has a set way of connection, we are not sure how to handle that yet. And for our second assumption to hold, we need fast synaptic dynamics, and it might be valid for slower timescales like we discussed for GABA B, which is on the scale of seconds. And as can be seen in our results, our method performs better in the low synchrony regime, because in the high synchrony regime, the independence assumptions about the Penning spike pools and voltage distributions might break. This is also a limitation of our network, of our framework. So that will be all. Thank you very much for this opportunity.